Hey, in another video we went over the basics and implementation of a ray marcher, and we ended up with a scene with a sphere on a plane. And you can make many cool things with spheres and planes, but there are also many other shape functions that we could look at. So I thought in this video I'll go over a few of the other basic shapes that we could be making. I also put a link in the description. If you are lazy or you want fast results, you could just copy paste them and they should work right out of the box. But if you want to get creative or you want to make something new or get really good at something, it's much better to really understand what's going on. So if you're interested in that, then stick around. So this is where we ended up last time, with a sphere on top of a ground plane. Let's go over the distance function for the sphere one more time really quickly. So we have our sphere over here and we have our point over there. And basically we just get the distance between the center of the sphere and the point. If this sphere is at the origin, then it's just basically the length of the vector for this point. And then we have to subtract the radius from that to get the distance to a sphere. Simple enough. So now what else can we do? So the next thing is a capsule. And a capsule is, you could see it as an extruded sphere. So basically we have two spheres, A and B, and then they're just connected somehow. And so the way to get the distance to a capsule is we could get the distance to a line that goes through the center of the endpoint. And if we get the distance to that line, then the distance to the capsule is basically the distance to this line segment minus the radius of the capsule. So we've done this a few times before, getting the distance from a point to a line segment, but let's do it one more time. So we can make a vector from A to P, and if we make another vector from A to B, and now we project this vector onto this other vector, and the way you project vectors onto each other is with a dot product. Then we get a number out of that, and we want that number to be 0 when this point P is hovering over A, and we want it to be 1 when it's hovering over B. And so, like, in order to normalize that, we have to divide it by the square length of AB. So now, like, this value T here is going to be 0 when my point P is hovering over A. It's going to be 1 when it's hovering over B. And it's going to be smaller than 0 when it's somewhere over here, and it's going to be larger than 1 when it's somewhere below B. And so now we can get our closest point on this line, because the closest point is just saying, okay, well, start at A and then go T steps in the direction of AB. So that is how we define point C. And now, before we get too far, we have to make sure that this point C doesn't slide past A or past B, right? We want this point C to stick to the endpoints, and that's why we have to clamp this value T to be between 0 and 1. And so now my C can never get outside of the line segment. And so now the distance is very simple. It's just the distance between C and P, and then minus the radius. So let's implement that. Okay, so let's go over here and let's make a function, call it float SD capsule, and that's going to take as an input my point P, and then my endpoints A and B, vec 3B, and then a radius R, so float R. Okay, and then inside of here we're going to make a a vector AB, so vec 3AB equals B minus A, and then a vec 3 AP equals P minus A, and then I have to make my value T, which is the dot product of AB and AP. So that's just like one vector projected onto the other vector. It's basically the shadow of one vector onto the other vector. And then I have to normalize that so that my T is 0 when it's hovering above A and it's 1 when it's hovering above B. So I will divide that by AB and AB. All right, so now I have that. Now I need to clamp this, so T equals clamp T comma 0 comma 1, so that my projected value can never fall outside of the line segment between A and B. And now I can get my point C, so vec3 C equals, we start at point A and then we go T steps in the AB direction to get to our point. And now we can get our distance, which is float D equals the length of P minus C, so that is the distance between the point C and point P, and then I need to subtract the radius from that. So, and then I could just return this. I don't have to put this in its own variable. So return. So let's try this one. So let me go over here and let's say float CD for capsule distance equals SD capsule, and then I'm gonna put my point P in there, and now I'm gonna have to find two endpoints. So I'm gonna do vec3, and I'm gonna put it at the same position as the sphere. So I'm gonna go 0, 1, 6. That is my point A, and then for my point B, I'm going to put something else that is fairly close to that. So let's think about it. Maybe it goes up a little bit, and it is at the same depth, but it also goes to the right a little bit. And then I'm going to make it a fairly thin capsule. So let's see if that works. And then so I'm going to take my sphere out and I'm going to put the capsule in. So I'm going to go over here and use CD. So let's see what that does. Yeah, okay, so it's not radius, obviously, it's R. So there we go. So there we have a capsule. All right, great. Next one. So a torus, or a donut shape. If we just imagine the torus to be at the origin, then it can just be described with two circles, or two radii of a circle. So like this is the first circle. I kind of drew it in 3D, so it's lying in the XZ plane, and then there is a smaller circle that revolves around that circle. And so how do we get the distance from some point P to the surface of that torus? So I put the point P here. It's actually above the XZ plane. That's why I drew a little arrow here, and it's casting a little shadow onto the actual plane. And so we want to get this distance and then subtract the radius from it. So in order to get this distance, if we could get this x and this y, then we can just use Pythagoras to get this d value. So let's try to get to these x and y values. So, well, this shadow that it's casting over here is the xz, or I call it point pxz. So the total distance from pxz to the origin is just the length of pxz, and then we subtract just the radius of the first big circle from that to get our x. So that's our x, and then our y is very simple because it's just a p dot y. So now that we have those two, we can make a vector out of those two. Like a vector 2, x and y, and if I take the length of that, that is this length d over here, and then I just need to subtract my second radius from that. So that is how you get the distance to a torus. So let's implement this real quick. Same way as for the capsule, we'll do float as the torus, and then it takes as an input a point P and a vec2 r, which is the inner radius, or the radius of the big circle and the radius of the small circle. And then we're going to write it out over here. So I'm going to do float x equals the length of p dot xz minus the big radius, so that's the x component over here, and then we can just return the length of a vector that I'm making, vector 2 with the x that we just calculated, plus the p dot y, which is how high like over the xz plane my point is, and then I have to just subtract my small radius from that. Okay, so now if I put that over here, so let's go after the capsule distance, I'm going to do float td for torus distance equals sd torus, and then I'm going to say p, and then I'm going to make a as a large radius, let's say I do 1.5, and as a small radius I do 0.5, and so we have that, and now we have to blend that in. And so I could replace this, but let's just add it. So I'm going to do d equals minus d and td. So what that does is that it will take either d or td, whichever one is closer to point P. So let's see what that does. So that gives me a torus that is obviously at the origin. Because we said before that the torus has to be at the origin. But if you want to move the torus, it's simple enough, because I can just subtract over here the point that I want the torus to be at. So if I subtract from my point P over there, let's say 0.0, comma, and then 0.5, comma 6. Then that point that is right underneath this capsule will get remapped to the origin. So that should give me a torus right underneath there. Great. So let's make it a little bit smaller here. So let's say over there. So now we have a torus, and maybe what I could also do is move the camera up a little bit so that we can see it a little bit better. So over here we had a super primitive camera. You can also make a more complicated camera, and then it's a bit easier to move it around. But for now, let's just say I'm going to put it a little bit higher above the ground. And then I'll make that it looks down a tiny little bit. So I'm going to do minus 0.2, something like that. Okay, so there's your torus. All right, next. So next up is a box, and if we define a box the same way we defined a torus before, where we say it's at the origin, and also, by the way, it's not rotated, so it's at the origin and not rotated, then we can just define a box with three numbers, namely the width, the height, and the depth of the box, or in this case, half the width and the height and the depth. And so how do we get a distance from point P here? So this distance d, well, if we can get this x distance and this y distance, then we can use the same trick as we used before with the torus to get this distance d. So how can we get this? Well, for the x, let's look at the x. So right now this p, because it's to the left of the box and the box is at 0, then this p would be negative. So if I just take the absolute value of p dot x, then I basically get this distance, right? I get a distance from point P all the way to this 0 line over here, and then I just need to subtract the x size from that in order to get this x over here. And in shading languages, you can do this on the x, the y, and the z all at the same time. I could just write this. So if p is a vector 3 and size is a vector 3, then it will just do that individually for x, y, and z all at the same time. So that's my length, that's my distance d. Now that works great for the point that I chose here, because the point that I chose is kind of diagonally outside of this box. But if this point P would be over here, then this function would essentially get me this distance over here, which is not what I want. So what I want to do is if this also for this point P, you could imagine that my dy would actually be negative, right? And so that's why. But negative doesn't really matter for Pythagoras because it gets squared. So that's why I get this distance. So what I want to do is, like in this case, I just want this distance, right? I don't want this distance. So what I can do is I can say, okay, well, like if any of my dx, dy, or dz gets negative, then just make it 0. And so if you do that, then this triangle kind of gets compressed to 0, and you basically just get the distance that you need. So there is your distance to a box. So let's implement that. Let's go over here and go float d box, and it's going to take as an input my point P and a vector 3s for the size, and then the first step there, here, so we're going to return something, and the first step was the absolute value of P, and then a minus s, right? So and the length of that, and that would be fine for all the way diagonal on the outside, but like if we're right in front of one of the box's faces, that wouldn't work. So we have to here say the maximum of 0 and that, so that so like what this does is it makes sure that none of the x, y, and z can get smaller than 0. If they get smaller than 0, they get capped at 0. So let's try that. So let's go down here and let's make a box distance. So float box distance equals distance box, and then no, I don't have to do that, P, and I can do the same trick as what I did before with the torus. So I do P minus vec 3, and then let's position it somewhere. So I'm going to position it at, let's say, minus 2, and then minus 2 and let's say 0.5 above the ground and 6 deep, and then I'm gonna say as a size I'm going to make it just a square box that is 0.5 size in every direction. And now I'm going to add that over here to the whole thing. So I'm going to do BD, and there is my box. So let's move it a little bit. I could move it a bit more. Maybe that's a bit too much. Something like that. And I'm going to stick it a bit higher off the ground, and then I have to make it a bit bigger too, so it's still resting on the ground. So there's a box. Okay, what's next? The last object I'm going to show today is a little bit more complicated than the other ones. Not that much, but just a little bit. It's a capped cylinder. So before we had a capsule, and you could see a capsule and a cylinder are kind of similar. That's why they have a lot of stuff in common here. So to start with, I just took out the clamp of this value t here, so that like t is not clamped between 0 and 1, and that means that c, the point c, is also not clamped. So this point c could move all the way like along an infinite cylinder. So if you just did this, so if you just took the capsule one and you took the clamp out, then you just get an infinite cylinder, which could also be useful for stuff. But we want to put some caps onto this cylinder. So how do we do that? Well, like the first thing to realize is that like there's a few different sections to this. Like if my point P is inside of the shaded section, then the distance to the cylinder is just this cylinder distance. We just need to make something else for if we're outside of this shaded area. For instance, if we're over here. So if we're over here, then we have to get this distance E, and we do that like very similar to how we did it for the box. So we need to just get an X and a Y, and then use the length trick to get this distance E. So and this X, by the way, is just my value D, right? Because the X, like it's just the perpendicular distance to the infinite cylinder. And then for the Y, it's a little bit more complicated. So for the Y, what I have here is this, and let's just go through this. So it's based on my T value, and if you remember, the T goes from 0 all the way to 1, right? And then it goes past 1 and it goes smaller than 0 over here. And so what this does is it folds that T value in a smart way, so that my Y value is 0 over here, and it's 0 over here, and it's smaller than 0 when it gets inside, and it's larger than 0 when it gets outside on either side of A and B. And the way it does that, so let's go through it real quick. So my T goes from 0 to 1, and then over here I subtract 0.5 from it, so that just takes the entire thing and shifts it. So now it is from so now I am from minus 0.5 to 2.5. I gotta see if I'm in the camera here. Okay, it goes from minus 0.5 to 0.5, and now we take the absolute value of that. So that makes it that the negative part of this gets folded over. So now I'm from 0 to 0.5. So that's this whole thing. That's the folded over part, and now I move that whole part to the left by 0.5 so that it's butting up against 0. I hope that makes sense. So now we have a value of Y that is negative inside, and it's like it's negative, but it gets bigger, and here it's 0, and then it goes plus. And the same way over here. So it's negative, it gets bigger, and then it goes positive. We have to, because this T value is normalized, right? So this T value, and what does that mean, normalized? Well, it means that this T goes from 0 to 1 regardless of how far away point A and B are. So we have to unnormalize it again, like, so we have to, like, so here we divided it by the length. Well, here we have to multiply it by the length in order to get this into the right scale. So that's the Y. And now we could do something very similar to what we did for the box. So we could just get the length, right? But then we had that same problem where it, like, if my point is hovering over the cap, then we don't want to get this distance, but we want to get the straight distance. Well, it's the same thing as for the box, so we just can use the same trick. So that is the exterior distance. And then one thing that I haven't mentioned with any of the other functions before is that there is the concept of an exterior distance, which is the distance to the surface from the outside of the object. But you also have something called the interior distance. And the interior distance, I kind of skipped over it on the other ones. For the box, for instance, the interior distance is actually kind of different. So for this one, I did want to go over it because sometimes you need a proper interior distance. That we'll go over it in maybe in another video, but for now I just wanted to define the interior distance as well. So the interior distance is it goes negative like 2, 0. So if you have a point that is just inside of the object here, then it's very close to 0, but it's negative. So just the same way as if you had a point that is just outside of the object, then it's very close to 0 because the distance is very close to 0, but it's positive. On the inside, like it's going to be negative. And the way like this is done here is that we basically have two distances, right? We have the y distance, which is the distance to the caps, which is the y distance to the caps, and then we have this d distance, which is the distance to the infinite cylinder. And then for any point inside of here, like we want to take the largest of those two values. And like remember that inside of the object, my distance is negative. So if I take the largest of those two, then I still get the number that is the closest to 0. And then I only want to do that for points that are inside, and that's why this whole thing is inside of this min 0 thing, so that if there's any point that is outside, then this will be larger than 0, and then this whole min 0 thing will make it that it caps it at 0. So this is my interior distance, and then like the whole distance to the object is the exterior distance plus the interior distance. So let's implement the capped cylinder. So for that, I'm going to copy the capsule because it's very similar, right? So I'm going to go over here. I'm going to say SD cylinder. Okay, and then let me just put this in right now before we build the rest of the function. So I'm just going to go. Let's copy this, put it over here, and now I have to say cylinder distance, I don't know, sil d, and that's my SD cylinder, and then we have to put it in a little bit different, otherwise it overlaps the capsule exactly. So let's see here. Well, actually, here let me just put it in first, and then because then we can see like when I position it. So I go sil d. Okay, so now it's overlapping exactly the other capsule. So let's move this forward a little bit. So let's say this is at 4, and then so we have something that sticks out now, and let's put it lower to the ground as well, 0.5, and then I'm going to put this farther to the right. No, sorry, that's not correct. Do here, farther to the right. So now I have it over there, and maybe pull it forward a little bit. I don't know, something like that. It's fine. And let's make it a little bit bigger too. So we have that. And let's make it a little bit lower to the ground. So it's 0.3, let's say 0.3. So now it's just lying on the ground. All right, so now we have a capsule there. So let's make that into an actual cylinder. So the first thing we can do is if I take this out, then you'll see that it goes infinite, which is useful for many things too. So that's a good one to remember. And now we have to come up with the x and y values, right? So this over here is actually our x value. So I'm going to go float x. So that's our x value, and then for the y value, we had that thing with the absolute. So that is the absolute value of t minus 0.5. And then that whole thing minus 0.5, So that was the normalized y value, and then to unnormalize it I had to multiply it by the length of AB, and then that's that. And then I could get the exterior length, so float E equals the length of the max of vector 2, that is x and y and 0. That should be it. So that's the exterior distance, and let me just try returning the exterior distance by itself. And so there we have it. It's already working, but you can see that there are some issues there, and the reason why that happens is because the ray marcher sometimes steps inside of the object, so it's a distance estimate, right? So it doesn't give you it doesn't know the exact distance. It can only get closer and closer with more and more steps, and so sometimes what happens is that it actually steps into the surface a little bit, and that is where interior distance comes into play. So if you don't have a proper interior distance, then you can get kind of weird things like this. So let's make the interior distance. So float interior distance is the min of the max of x and y, and then 0, and then we have to add that, so plus I. Let's see what that does. And you see that let me just stop it over here, that made it smooth. So for the box, for some reason that isn't an issue in this case, even though the box interior distance is not completely correct the way we have it. So obviously adding something like this, it costs instructions, right? Like there's a performance penalty for this. So if you can get away without a proper interior distance, then I recommend that you just don't do it. But in some cases you need it. In this case we needed it, so that's why I put it there. So with these primitives, you can do a lot. So most of my shaders, they actually only use spheres and capsules, and maybe sometimes a torus. I don't think I've ever used a cap cylinder or a box, but I imagine that if you wanted to make stuff like buildings or stuff like hard surface type stuff, and then a box could come in handy. There are more shapes that you can make, although these are definitely the most useful ones. I hope this helped you, and I hope you like this. If you do, like, comment, subscribe, and I will see you next time.